Okay, so for this question, we really want to draw our diagram first. So we have a mass here. We know that our mass is 100 grams, and we know that it's hanging from a spring. So what I've drawn here is I've drawn our three different situations. So we know that on the right-hand side, we know that this is our equilibrium position. So our mass is sitting at equilibrium here, and we know that x is equal to 0 at that first diagram. Our second diagram is essentially showing what it says happened. The spring was pulled down 40 centimeters. So I've put here negative 40 centimeters because we're pulling it in a downward direction and then it's released. The third diagram is showing what is happening. So we want to know what the speed is at that point. I also put in a few other things. So we know that in this second diagram, we know that our force restoring is going to be pointing in an upward direction. That means we know that that force restoring has to be positive in that second diagram. In the third diagram, we know exactly the opposite. Because the spring is above, we know that our force restoring is going to be pushing down. And because we know our force restoring is pushing down, we know that we also have our acceleration, which will be going down. That means that both that force restoring and our acceleration will be negative in our third diagram. But we also know, and my diagrams aren't to scale, but we know that x is 15 here and x is 40 here. And our amplitude, or our max displacement, it could be the same. So that means that we know that on this diagram over here, it could still be pushed up if it wanted to be, or it will still be pushed up. So we know that our velocity is still going in that direction, and these should all be vectors. But we know our velocity is still going in a positive direction. So we know that our velocity in this case has to be positive because the mass would still be moving upwards. I've just taken the diagram and I've squished it and put it up in the top so I have a little bit more room for my math. So what we know about this question, I've written up here at the top, we know that we have 0.1 kilograms and we know our spring constant, which is 1.014 newtons per meter. For A, we also know that our F net is the exact same thing as our FR, or our restoring force. We know that our F net, because F equals ma, we can say that our F net is equal to ma, and we can say that our FR is equal to kx. In this case, because we know over here, where I'm underlining in red in the diagram, we know that our force restoring and our acceleration have to be negative. So we can say here that we know that our force restoring has to be negative and put in our negative sign. We can rearrange this for A and we can figure out our acceleration at the point of 15 centimeters, which is what we're asking for. So when we rearrange for A, we are going to have that our A is going to be negative kx over m. We know our k. We have negative and then 1.014 newtons per meters. What we want to do is we want to figure out what the acceleration is at the x of 0.15 meters. And we want it positive 0.15 meters. We're going to divide that all by the mass, which is 0.1 kilogram. And we will get an acceleration of negative 1.52 meters per second squared. Notice that our acceleration is negative, which is what we need it to be because it should be accelerating in a downward direction. What we're doing is we're looking for maximum speed. I'm going to do it in red. And we know that the maximum speed is going to happen when it's at the equilibrium position. Doesn't matter if it's moving up or down, so direction doesn't matter. But we know that it's going to be right here in this situation when it's at equilibrium when x is 0. So our formula for this is what we just figured out is going to be Vmax equals our amplitude, which in this case is going to be our 40 centimeters, and then the square root of k over m. We will put in our numbers here. We will have 0.4 meters multiplied by the square root of 1.014 newtons per meter over our 0.1 kilogram, and we have to take the square root of all of that. We will get an answer of 1.27 meters per second. And again, the direction doesn't matter a lot here because when it's going in a downward direction, it'll be negative. When it's going in an upward direction, it'll be positive, but the velocity will be the exact same at equilibrium either way.